So our talk's going to be about some experiences we've had with using graph databases for reverse engineering, and it was something that I, first got interested in because we ended up acquiring a company where we have a lot of guys who are very experts in this type of stuff, and so they started talking about how to use it and what they're doing, and just the idea started running. And I started talking to Jasiel, and that's kind of the genesis. So we'll go over some of what graph databases are. And then some how they differ from normal databases, and then also talk about some examples and some real world examples and where we want to go with our own work in the future. So I'm Jason. I'm a senior security research analyst at Arbor Networks. I used to work with Jasiel when we were at Tipping Point. It's now owned by HP. I primarily reverse engineer malware all day. And so I have a lot. Arbor Networks is a DDoS company, so I do a lot with DDoS and DDoS botnet tracking. Then just dealing with malware, we always want to know you don't want to reverse the same thing twice. So we try to figure out ways to automatically identify similar samples so you can just kind of skip past it. We also have some side interest in bug hunting and vulnerability analysis and automating reverse engineering. And I actually have from an undergrad, then a little bit past that, I have a strong math background where I actually did a lot of work in graph theory. And so, taking something that I was able to do way back then and reapply it is very fun for me.
All right, I'm Jasiel Spelman. I'm a security researcher with HP's security research team. I'm also a member of the Zero-Day Initiative, where I analyze and vet vulnerabilities that are submitted to us. I've been interested in static analysis ever since my boss's boss, Scott, kind of derided me for doing things too dynamically. We then took binary literacy by Rolf Rolls, and that further piqued my interest in static analysis and reasoning about a program and different ways to look at it so that you can, just get a better feel without having to run it over and over again. So we're talking about graph databases, but first, what exactly are those? Who's kind of in the title. It's a database of a graph, where a graph is a collection of nodes or vertices and the links between them or the edges. A graph can be directed, so you could have, say, a link that goes, a edge that goes from one direction to another but not backwards, or it could be undirected. You can also have cyclical or acyclical, where it potentially goes back to the same node over and over again, or goes to some other node that then returns back to you. One of the nice things about graph databases is that you can take advantage of graph theory that Jason and I both learned while we were in school. You can apply it in a more formal way and get a better idea of how a program is executing, because a program is kind of like a tree graph-like it kind of has a tree graph-like structure. You can do this with a relational database, but you don't get the benefit of having all that code written for you. You have to implement all of that on your own. Whereas with the graph database, even if the graph database is implemented on top of a relational database, you get that for you. These are mostly written in Java. For whatever reason, that's the big data language, and that's just something you kind of have to accept. So graph databases versus relational databases. Relational databases are the tried and true manner of storing data. Individual data units, the smallest data unit is a row. You could argue that it's actually a column within a row, but for our purposes, we're going to say a row. Relationships between two different tables are defined against the table. So rows in table A are related to rows in table B by some column that they share or multiple columns that they share. Graph databases are very different in that the smallest individual data unit is a node within the graph. Relationships are done against the individual node, so one node can have arbitrary relationships, whereas a node that it's related to can have completely different relationships. An example of this being, say we were to take a look at attendees versus speakers. In a relational database, we could have that mapping done in one big table, whereas in a graph database, you'd have to define it for each attendee and each speaker. As a result, it's entirely It's far more space intensive than a relational database, but when you're looking at specific sections of a graph, you're able to get more information and do things a little bit more quickly. And now I'm going to turn it over to Jason.
Now we're going to go over some existing graph databases and talk about potential applicability to reverse engineering. The first one is Maltego. Hey, do you have a typo on who it was created by? But it's something, if you've done reconnaissance work or kind of open source intelligence gathering, you've probably seen it. You'll see like those bubble graphs where the more edges that go into something, you can have it like grow larger. You can also actually do it by outbound edges or weights of the edges. So that's actually from a graph I created from another talk where I was actually showing relationships between different C2s that were ordering DDoS attacks against some targets that we were investigating. And so it's good for intel gathering and correlation. So it's been around for a while. It runs on Linux, Windows, and Mac. The downside is that you do have to install Java on your Mac. But for reversing, it's probably not that great of a thing, mostly because scalability-wise, I've had issues with just putting in IPs and host names and MD5s and linking them together on the order of thousands. And then when you're talking about loading some like a large binary in there, you're talking about if you want to make your vertices a basic block, then you're talking about tens of thousands of basic blocks in some of these larger programs. So it's probably not the best case, but it's it's one that's been around for a while, and I think probably most people are somewhat familiar with. But there's another one called Titan Graph, which definitely has a much better chance to be applicable to reverse engineering. A company called Aurelius, and Marco Rodriguez is like the main architect of this database. And he's a really smart guy, does a lot of work in graph theory. It's designed to handle large-scale data so that you can actually have a Cassandra cluster on the back end, or you can use HBase, or so they have some other database support as well. And so when we're talking about scalability, if you've ever loaded MS-HTML or MSO into IDA and you know how long that takes, it'd be cool if you could have something offline to crunch that and then throw it into like Titan and actually do operations on it without having to sit there and churn through it in IDA. They have a query language called Gremlin, which is a pretty cool query language. I have some examples of on the next slide. But it allows you to select nodes based on properties and then filter them down further, and then find other nodes and edges based on other properties. So he has multiple language support. Rexer is a REST API that sits on top of Titan. And so there are a couple of Python modules that I've used before one's called RexPro, one's called Bulbs. I kind of go back and forth on which one I like more. The coolest one was called Thunderdome, just because of the name. But unfortunately, it hasn't been updated for a while, so it's probably dead. It's my current favorite one, mostly because I've used it for a lot of passive DNS and malware domain correlation. But there are some limitations, like if you create a graph and you want to index a property, when you create that index, unlike with a relational database where it back indexes everything, it only future indexes. So you really have to think about what properties you want in your graph before you actually start creating your graph. And so you can also do like lists and hash maps and stuff in the type. So you can actually have a list of all the variables in a specific basic block attached to a vertex type stuff. And so Gremlin, you can see here, Titan is they have a very Greek god theme to it, and their examples as well. So like right here, they're searching for all the out edges from Hercules. What's he battled? Okay, now show me all the properties for those things. And then they filter down the next time where they're looking for filtering it by time and then just selecting specific properties. And then they actually go through and they say out edges, and they actually rename what the property is going to be in the printout, and then they just select down further. And so I've used this to actually build like a massive passive DNS graph databases where you have a host name that has a bunch of A out edges or C name out edges or quad A out edges to IPs, and you can actually start traversing that down to an IP and then like going back and then potentially finding relationships between them. And so then I was doing that, I started thinking about how could I apply that to reversing. And so that was kind of one of the interesting things with Titan. And this is one I just learned about called GraphX, which is part of the Spark project. And there is a way to connect Spark to Titan. Spark is kind of seems to be talked about as a replacement for Hadoop. Like Google yesterday in their I/O conference actually said that they are no longer using MapReduce jobs internally to process data. So Hadoop is really built around MapReduce, but MapReduce is a hard thing to write jobs for, and Spark is supposed to be much easier. So you can write stuff in Scala, Python, or Java. We actually have some guys who are doing a lot of stuff in Scala, but it's cool because they can write their stuff in Scala and they can expose the interface to me. Then I can write everything I want to do in Python. And then GraphX is the graph processing portion of Spark. And so they say they want to merge data parallel and graph parallel. This is kind of a weird semantic argument around that I don't quite understand, but it's still very new to me. And then they also have a bunch of just algorithms you can use by default. So PageRank seems to be the most common example algorithm that a lot of these graph processing libraries include. So I'll turn it back over to Jasiel.
All right, so Jason had mentioned Gremlin and Rexer. Those are both part of Tinkerpop, and Tinkerpop is basically just a collection of frameworks. If you're going to use a graph database, it's in your best interest to use something that implements at least the Blueprint's common interface, because that makes it easier to switch languages or switch graph databases if you find after implementation that your graph database is just not holding up. So as I said, Blueprints is a common interface. Gremlin's a query language that's kind of Groovy-esque. Rexer is just a REST API so that you can access everything from other languages. Furnace is a collection of graph algorithms, and best analogy I can think of is the algorithms library from the C++ standard templating library. Frames is a graph object mapping. If you're familiar with Ruby on Rails or Django, then you may have heard of object relational mapping, and that's basically that, but applied to a graph, so that you can define nodes in a graph as objects in Java or whatever language you're using. And then there's pipes, which is it's just for data flow, for merging, intersecting, or filtering out your result sets. So Neo4j is another one of the graph databases, and it's my personal favorite because of the query language it uses. It's very SQL-like. It's also one of the more mature graph databases. It's been around since, I want to say, 2007. Unfortunately, it's single server node only, so you're kind of limited to what hardware you can throw to a single physical box or single virtual machine, whatever. Here you can see an example of what Cypher query language looks like, and you can see that if you're familiar with SQL, it'll look kind of similar to you. Writing queries for it is very straightforward. Next is BinNavi, which I'm sure many of you are aware of and probably have used. It's created by Dynamics and now owned by Google, and Halvar has tweeted out, or at least hinted, about possibly open sourcing it, but for now it is a commercial product, so you do have to pay for it. It uses Postgres as a backend and imports data from IDA and allows you to better visualize an application. But you are still limited to the schema that they've defined in Postgres. And then next is IDA, which almost everyone should be aware of, and defaults to a graph view, the control flow graph that it makes it easier to look at a function and know basically what the function's doing. Because just based off the graph overview, you can see if-else conditional, switch statements, whatever. All right, now that we've gone over graph databases, how does this actually relate to reversing? You can treat basic blocks as nodes within a graph, and you can treat calls and jumps as edges. You can attach, for jumps, you can attach what type of jump it is or what the conditional is based off of as a property to that edge, so that you can then do further filtering on it when you're trying to do any sort of pathfinding or really anything. It also makes for a nice data store that you can query from IDA or Capstone or whatever you're doing as you're doing your reversing. And
now we're going to go over some ideas we have for some applications, and then a few work in progress proof of concept tools that we've been working on. So the first one was taint tracing. This actually came from Stephen Ridley tweeted out talking about Capstone and how it would be really cool if you could load Capstone into Neo4j and then to use that to build a graph database and then apply some taint tracing algorithms to it. And then I actually started having a conversation back and forth with him about graph databases, and we both started talking about, yeah, it would be really cool if we could do this, but we don't really have the time right now. That's actually kind of where the idea for the talk came from, because I went and asked Jasiel, like, hey, do you want to like try to throw something together for REcon? And it was like, he's like, sure, and it's like, great. And so then we started working on it more. And so I've actually haven't worked with Capstone a lot, but I've been working with it more recently. So I'm still I can still, start disassembling, and I'm working on like my own basic block construction algorithms. And they're still not perfect, but on most functions I can actually get basic blocks. I can load that into a graph database and apply it, put edges in there, and then start adding some properties. But I'm familiar with taint tracing. I understand what it is, familiar with the concepts. I haven't really done it much in practice, mostly because I operate more on the malware side instead of on the vulnerability bug hunting side. So I haven't quite gotten to where I can actually create a full proof of concept for this. But it'd be nice if you could actually take in, like, say, an update from MS-HTML or just any application has an update, crunch it with Capstone, load it into a database, and then start running through it and say, hey, I'm interested in this function that was changed, and I want, like, this data comes in from the network, tell me where all it's touched, and see if we can determine if there are any vulnerabilities in there because of that. That's definitely something I want to get to in the future, just not there yet, personally. And then the other idea is something along the lines of code identification. Because you have graphs and you have graph structures, you can actually do comparisons between these graph structures. And bindiff, that's one of the parts of bindiff that does that. I actually use bindiff a lot to kind of compare old IDBs that I have to new IDBs if I think some malware is related to each other. So I can end up saying, hey, this is just the same function. But it'd be nice if we could actually do some graph isomorphism routines to identify these structurally similar, and then add in some kind of fuzziness for the fuzzy hash type stuff to say, yeah, these basic blocks are pretty similar, and then just start being able to use code identification like malware descendancy, or even for me, that's where I'm interested in. And I know Jasiel has other interests along that lines, but in malware, one of the most common encryption routines you see is RC4. It's very recognizable. If you've been reversing malware for a while, you can look at it in IDA in just plain text mode, and you can say that's RC4. You have one loop that goes for 256 iterations, followed by another loop that's 256 iterations, followed by another loop that's a length of the string, and then with some XORs. And so, but I started working on POC for this, but I ended up finding that when I was doing it in Titan, I couldn't figure out how to really compare two graph traversals inside of Titan itself. So I ended up pulling all the code back into Python, which kind of meant that I just constructed this own thing in Python that didn't need a graph database. So I ended up abandoning that proof of concept. And then I moved on to mutational fuzzing. And so, a lot of file formats are graph-like, or you can kind of make them graph-like. So like, HTML file, you have HTML as the root node. You have head and body just as children. They can have other children. And so, and some aren't, but then you can just kind of just have them as a straight line if you want to do something like that. So then you can build something to parse these file formats, load them into a database, and then use that corpus to fuzz against. Like you have up here we have the MP4 atom structure. And so you can actually, I ended up using this as a proof of concept where I had some code to parse the MP4 atoms and then load that into a database and create a basic structure in the database that I could then walk down and potentially use to generate some files, legitimate files. But you have some structures that are kind of a pain to parse, something like PDF that's just kind of gross. That if someone wants to do, it'd be great, but we don't really. Yeah, that's a huge pain. So you can also do something like this, like network protocols with the structure. Some network protocols, if you want to fuzz like some kind of binary protocol that an application uses. And so this is the POC I generated. This is the graphical representation of it. So Titan doesn't have visualization built in. So I connected Gephi, which is a graph modeling program, to Titan and pulled the data in. So you see I have the master node, and then I actually ended up coloring the nodes and the edges based on the types. And you don't see it here, but like most of those have like other properties like bytes associated with them. And then all those edges are of type children, and then the children actually have an order applied to them saying you have to add these in this order into a file. But you could also have it say these orders should be random. Like, hey, randomize this, see if that changes how it gets parsed. And so I have it loaded into the graph database, but I haven't yet generated actual fuzz files with that. So last one I'm going to talk about is just kind of the idea of collaboration, sharing, or even just reuse of your own databases. It's been done a lot. Nothing really seems to have stuck. I think CrowdRE is still the one that's still in existence and being used, but I have issues with the data licensing with that, so I don't want to use CrowdRE for some of my stuff because I can't share everything I do. My work would get very mad if I did that. But it'd be nice if you could use IDA to load, basically kind of copy it up into a graph with all your comments, your variables and stuff, and then pull it back in. I do this a lot with BinDiff, just to say, hey, this is a new variant of a malware. Just add in all the old stuff, and now I can find the new stuff really easily. But then we also have times where, person A reversed this malware like 2 years ago. They're gone. I have their IDB. I have to find their IDB to dip it into mine, and I end up having to reproduce a lot of work. Then there are also cases of software that at one point shipped with symbols and no longer ships with symbols, so you can at least recover some symbols from that point. So now I'll turn it back over to jasiel.
All right, so one of the main things I'm interested in is pathfinding. One of the things that graph databases excel at, and IDA does actually have this functionality, and from a graphical standpoint, you can do extract to or from, and you have some ability to filter, but it's not as fine-grained as I would like. From a IDA API standpoint, there are options in the IDA API and IDA utils Python modules, but you still have to then siphon through and have all that logic done in Python, and it's kind of slow, especially for larger binaries such as MSO or MSHTML, like Jason mentioned. The code was supposed to be on GitHub, but I didn't bring the creds with me, and I only have a burner laptop, so I'll make sure it's on GitHub on my GitHub page as soon as I get back into town. But in the meantime, I can show you basically here is a query that gets generated, and in the Cypher query language, we're specifying that begin is some node that matches a function that has a name of sourcefunc. End is some node that matches a function that has a name of destfunc. And then we're looking for any path that starts at begin, ends at end, and has a length of anywhere from 0 to 10 edges. And we get a result that looks kind of like this, where the orange nodes are all basic blocks, and the purple nodes are all basic blocks that are also function heads. Obviously, this is a small example, but it could be used very, very nicely. You can easily add more constraints to this. Part of it would require more intelligent importer code, because right now I am just importing the basic blocks, but that alone could be useful. Say you're looking at a large binary, and you see that it has a common set of input sanitization routines. You could then enumerate all the entry points that take in user data, and then try to define some function you want to reach, and have the graph database try and find a path from the entry points to the function you want to reach that does not go through the input sanitization routine. And from there, you could then statically look and see what you could do. As kind of what's been published out there and is more of a finished work, there's Journ by Fabian Yamaguchi. It's a source code analysis tool, and as that implies, you have to have source. But it parses C and C++ into an abstract syntax tree, and then creates definition use chains for all variables. It uses Neo4j, which is another reason I kind of like it. Some of those dependency chains get broken when it gets to imported functions, but you can get around that by tainting arguments so that you can specify that a particular function call will result in that data being, or that variable being redefined or reused or whatever. So as far as what's next, there's, Journ has actually been used to find a number of vulnerabilities in the Linux kernel. I think numbers around 18. As for what's next, I want smarter import code. I do a lot of stuff statically, and being able to pathfind to get to a particular basic block or a particular function is vital for me. I also have code that uses Pin and DynamoRio to collect hit traces for dynamic function calls, and merging that in with this would allow me to better find paths.
And so, as far as where I want to go with it is, I want to create more, the file format type parsers to generate corpi of large, legitimate files. Like the example I showed earlier was actually one of the MP4 files that Hugo released from REcon last year. Was the Microsoft Radianov talk on gaps. So it was kind of like cool that I was able to use it from something I actually had watched. But now I actually need to go back through and be able to generate these fuzz files to actually use that structure tree or the graph data that I'm creating. And then I'd love to actually figure out how to do some of these comparisons inside of a database. And part of that's also that I kind of need to settle on one database. So every time I find one, I'm like, oh yeah, this one is cool and has a lot of features and has this feature this other one doesn't have. I go to that bit, oh, it doesn't have this feature this other one has that I kind of need to do what I want to do. So I haven't really settled on exactly what I want to use yet. And then, keep also once I can do that, then potentially finish up the capstone code and start working on some of the taint tracing stuff. And that would also be quite a bit of fun. So just to wrap it up, it's these graph databases can actually be used for lots of fun stuff in reversing. It's the barrier to entry is pretty low because you can run something like Neo4j on your laptop. I actually have Neo4j and Yarn running on my MacBook. I had Titan running on it too, but once you start scaling up, you have to go from a MacBook to server. I have a Titan server running on a server that has 72 gigs of RAM and a couple hundred gigs of storage right now, and I still kind of hit performance problems because there are a lot of gotchas, but it can be resource intensive and also Java intensive. So that we'll have take any questions.